Thank you so much. It's a great pleasure and privilege to be here and to interact with so many people. I want to extend a warm thanks to Dr. Shyam and all the people at the planetarium, as well as the observatory and at the physics department for charting out such a packed but exciting set of events over the next few days when I'm going to be visiting here. And I already had the pleasure to visit some of the departments and so on, and it's great to be here and interact with you, the public, on some of the most exciting frontiers of cosmology, of astrophysics, which I've been involved in over the last few years. So as you can see on the first slide, the talk is going to be on mysteries, deciphering, solving some mysteries from the invisible universe. Now, invisible because we are going to think about the radio wavelengths, which are not visible to us, to the eyes, but nevertheless, they carry a lot of information about cosmology, and especially this period which is known as Cosmic Dawn, the place, the time when the first stars and galaxies lit up our universe, literally. So this is just a caricature of that. And we will learn that a large amount of cosmological secrets can be unveiled at this epoch by radio frequencies. So just to set the stage, I thought we will start with a little bit of introduction to what we have here. Many of you may be familiar with some of this, but the landscape of our universe, the structures, the sizes, the distances, what are we talking about here? So the first thing to note is that we are going from, let's say, the whole realm of distances, microphysics. Of course, most of us are familiar with viruses, more so in the last few years. So the viruses and so on are 10 to the minus 8. That is 1 divided by 1 followed by 8 zeros, measured in meters. So we are all familiar with meters, and in our daily life, we are used to few meters, few kilometers, so on. This is 1 divided by 1 followed by 8 zeros, a very small amount of distance. And these are all in the realm of microphysics, whatever you can see on that end. And in astronomy and in cosmology, normally, if this works, I will use it, we use the opposite. So we use the opposite end of the spectrum. It's more like the distance to the furthest quasar, the furthest galaxy, furthest planet, and so on, which are, as you can see, 2 into 10 to the 22, 10 to the 16, which is 1 followed by 16 zeros, 22 zeros meters. And normally one doesn't want to write so many zeros in our day-to-day life. So instead what you do is that you call something as a light year or parsec, which is like a galaxy scale, and that's what is written here. And most of the time you say in units of light years, the distance that light travels in a year, 10 to the 16 meters. So 1 followed by 16 zeros, these things become more manageable in those units. Now I'm going to take you through a short voyage, which I hope it works. I'm going to try to be a little fast through it, but we can discuss it later when it is at the end, through both space and time in these sizes and distances. So as we have seen, so I hope this works. This is a movie which you will see starting from the Earth. So we are going to start from the highest peaks, let's say the Himalayas, and then go ahead and further out and into really the realm of astrophysics and cosmology. So maybe the lights need to be a little dimmed here to see it, but if people can see it at the back, that is fine. And you'll see that as we move ahead and ahead, you are going to access out of this Earth through all the continents. You're seeing planet Earth, and you're seeing it against the backdrop of what is to come. Now, as you move ahead, you're going to see that stars are beginning to appear. There's the backdrop of the few stars which we recognize, and many of you will, as amateur astronomers, might even know some of those. But first, we have to go through all these artificial satellites. As you probably know, the Earth is surrounded by a large number of objects, sometimes space trash and things like that. So there are lots of things which are kind of contaminating the view. but those are going to be also very useful things like satellites and so on, which are there for telecommunications. And we keep going ahead, and you can see that the sun becomes clear in the backdrop. And as we know that we are in a solar system, a system around the sun, you can see that the sun is becoming clear. Now it's about, you can see down, light travel time is 1 second. So 1 light second or a few light minutes is where we are right now out of the Earth. And then comes into view the orbits of the planets in our solar system, Mercury, Venus. We know all those planets, Mars, Saturn. We are back to 1 hour light travel time. We are zooming out. One day, we see that these constellations you may recognize, the zodiacal constellations, some of you again who may recognize this in the night sky, and you see that this is like the sun's brightness and the light travel time is about 1 year. So this is like a zoom out. Here we'll pause and we'll look at these stars. I think most of you might be familiar with some of these. Proxima or Alpha Centauri, that is kind of the nearest star system to us, about 4 light years away. Now you see that this map is like a Google map. So you have, this is a distance which is a scale, and that is about 10 light years. And you see that all of these are the nearby stars. For a cosmologist, this is our local neighborhood. This is just a backyard. This is like, you know, our own systems. You'll see an arrow, and this arrow is pointing us to the galactic center of our galaxy, which we are going to see as we move ahead. These are various stars. There are also some comets. There are various things which are there. But now you can see, this is important, the humanity's first radio signal. So we can get radio signals from something like 70 light years away. So 70 light years is what we have. And then we go and we have seen this beautiful galaxy, which of course is not a photograph. We cannot photograph because we are sitting inside. So this is just an artist's conception. And here we are out of the galaxy around 100,000 light years from this where we started. Here's our galaxy, and our galaxy is about, you see, 10 kiloparsec. Now kiloparsec and kilo light year are roughly equal. For this talk we can consider them to be similar. So you have 10,000 light years. That's the size of our galaxy. You can see that our galaxy is beautiful and it has spiral arms. It's a very common galaxy. Many galaxies have that. And you have different kinds of names of those, and you have different other galaxies and dwarf systems and so on which are there around this galaxy. And again, this Google map is showing you the scale is really high. We have zoomed out and come. Now we will go a little bit further, and we go all the way to neighboring galaxies. So neighboring galaxies, we should keep in mind, the main thing is that they are about 1 million light years away. So light travel time, for instance, to the nearest galaxy, about 1 megaparsec. So that is 1 million parsec or something like million light years. This is a photograph of our nearest galaxy. It's called Andromeda. And it has a lot of interesting properties. It also has some other systems around and so on. And this galaxy, most of the time, these galaxies are 1 million light years away from each other. We'll go a little bit more out. You see 1 million years here, and we are going out. What we have to realize is that today's cosmology, today's data sets have mapped a large fraction of the nearby universe. Now, nearby, I mean up to about all of these and almost 5 billion light years away. So you can see each dot in this picture which is coming is one galaxy. And there are infinitely so many dots. And these are regions which our surveys in cosmology have actually mapped. They have provided us extremely fine maps of the galaxy. Whatever is not there is not that there are no galaxies, it's just that there has not been a map done in that part of the sky. Now we will go and understand that this is one of the most interesting consequences of this data set. This is called the Dark Energy Spectroscopic Instrument, DESI, which is like the most latest galaxy survey, which is now going to map about 10 million, 14 million galaxies, and this is just a small snapshot of what it has done so far. And you can see one thing which is clear to everyone, that on the largest scales, like on the scales which we are talking about, The universe is smooth and it is isotropic. So what is that? You can see that generally wherever you look at these kind of scales, you see that there is not much change. So it's called homogeneous. It's like a smooth, kind of piece of paper, and also isotropic. Isotropic means that no matter what direction you look, you are going to see round about the same thing. So it's on an average statement that this is one of the biggest cosmological lessons. It has been proved by observations all the way until today. This is just something that tells you that the light which is there goes all the way to when the universe was extremely young. So what we are going to see at the end of this, which is going to stop a little bit, but the light which is left over from the Big Bang forms a horizon. So it is known as a cosmic horizon in both space and time, and it's called the cosmic microwave background, and that is really the oldest light from our universe. It is almost light from the Big Bang, and that is the limit of what our surveys are going to see for us. So let's go ahead and say what are the lessons we learned from our cosmology so far. The most salient one, maybe we can call it the discovery of the 20th century, is that the universe is expanding. This is something many of you may have heard of, many of you may have come across, and it can also be misinterpreted in many ways. So here I am going to tell you a little bit about this statement. It's called Hubble's law. The main thing to remember is what it means is that almost all, Andromeda and us are actually coming together and going to collide in another 5 billion years, but in large scales, at the very large scales, most of all the galaxies are flying apart from each other. So just to qualify this, we are going to look at these statements. Those of you who have been in, use these Bunsen burners, or in laboratory, you have these hydrogen lamps, yeah? So this hydrogen lamp, you have always something called a spectrum. From the hydrogen lamp, you have light, and usually you can measure this spectrum. You must have done it for many things in the lab. You have some light and you can say it has certain emission lines. Now whenever you see this kind of emission line, you know it's hydrogen because it has a fingerprint, like no other element will emit in this way. So at rest in the lab, this is what you see in hydrogen. And when you have a cosmology or astrophysical hydrogen, people have measured, people have seen through the telescope spectra, and you can see that the hydrogen is just like in the lab from the nearby sources, nearby galaxies, you see that hydrogen is present. However, when people started looking at very far away galaxies, they found the same spectrum but moved to the redward side. So the wavelength increased, and it was exactly the same lines but red shifted. It is called as displaced. And we found that more and more further galaxies, more and more is the shift to the red. And as we go higher and higher, it is something like a Doppler effect. So it is not exactly Doppler effect because we have to bring in the laws of general relativity, but it is something like the galaxy is receding, is moving away from us faster and faster. So what it all tells you is that as galaxies are further and further away, they are actually moving faster and faster away from us also. So this means that this is the evidence for an expanding universe. So this is called as redshift, and you see that at a very high distance, the hydrogen is very red shifted. And this is something which people sometimes also confuse. So the main thing is that all galaxies are equal. It's not that we are at the center of the universe and all the galaxies are going. Every galaxy will say that. So one should think of this as some kind of cake or bread with some raisins or something on top, that when you expand the bread or you expand a balloon with a lot of numbers on it, everything will move away from everything else. So space itself is expanding, and it is not like some galaxies at the center and everything is moving. No. So the Big Bang took place everywhere in space and in time, and the universe is expanding completely. So there is no center to the universe. That is the main thing. Now, three consequences of this particular statement leap to the eye immediately. First is that the universe has a past. because it was expanding, so there has to be a history to it. Sometimes people used to think that it was always static and so on, but we know now that the universe has a past. And it was smaller in the past because it is expanding, so in that sense its size was smaller. With theoretical physics, one can show that the amount of material or matter in the universe has roughly been constant through time. And therefore, we can say it was denser in the past because that material was packed into a smaller size. It was also hotter because the standard laws of thermodynamics allow you to describe the thermodynamics also of the cosmos, and you can show that it was hotter in the past. Most importantly, there is a theory which allows you to exactly describe, and that is one of the biggest successes of cosmology, that right from the time the universe was about, you see this number, 10 to the minus 32 seconds, 1 divided by 1 followed by 32 zeros, that much fraction of a second, till today, we almost know all the physical processes which have there in the universe. We still have to work out some things, there are challenges and so on, but what we don't know, what people call as, you see the first part is something like people call it Big Bang. Big Bang is just a name, there is nothing which was banging or anything, it's just that we don't understand the theory of physics in order to formulate that small period of the initial part of the universe. I am talking below 10 to the minus 32 seconds only. After that, before that, we had to bring together the quantum mechanics and gravity, which is still an unsolved problem. So that is why you don't have that. But after that, we know exactly when the light elements form. That means hydrogen, deuterium, lithium, those elements, they formed a few seconds to minutes. Then we had this cosmic microwave background I told you, which is the horizon, the light from the Big Bang, that has separated from matter at an interesting time, which is here called parting company, when the universe was about 300,000 years old. And you see that this is the radiation which is coming to us all the way from that time, all the way to today, 15 or 14 billion years. Finally, you had something called the first light, cosmic dawn, or the galaxy formation, and this is the era of direct observation, what we can see right in front of us, right with our telescopes today at James Webb and so on. So if we want to collapse all that, what I told you, into one day, so let's say that the universe is happening in one day, how would it be? So if you see the Big Bang, suppose was 12 o'clock midnight, then various atoms etc. have formed within a minute. This is an important period, something like cosmic dawn, which is when the first stars formed just after half an hour. Then everything else which we know took lots of time. Sun is born 4 p.m., 4:30 p.m., Earth, etc. All those things are much, much later. And if you see, the human beings are very, very recent in our universe. They are almost at the next day, and the present day is just on the next day. It's the 12 midnight. So we are very new compared to all the stars and cosmic dawn and all those things. And of course, the sun will eventually become what is known as a red giant. It will eat up the solar, but there is time for that. It's only at 8 a.m. tomorrow in this. So one of the things which we want to understand with all this cosmology, and which are kind of open in our understanding, are firstly, of course, how did this galaxy formation happen? What was all about this cosmic dawn? How did these first galaxies form? And how did they, impact the universe? That's very important. Second, of course, a very popular one, I think most people here will be interested, are we alone? Is there other intelligent life around the universe, and can we hope to make contact with that? Thirdly, and very important one now, is, was Einstein right? Now the reason is the general relativity is more than 100 years old, and we have now about the time when we can really test the general relativity theory with the help of various cosmological precision measurements. So that's an important question also. Now the first question, which is about the galaxy formation, we can answer very almost comprehensively, because the reason has to do with the flow with gravity. People like to say in cosmology that gravity is the ultimate capitalist. The rich become richer, the poor become poor, because whenever you have a little bit of mass and no mass here, this mass will attract all the rest of the mass towards. So it will become bigger and bigger, and the rest of it will become much, much smaller. So therefore, the smallest fluctuation, so what we saw in this oldest light was that this light was not fully uniform. If it was fully uniform, nothing will have come out of it. But it had some small little differences of temperature and density. So therefore, this density, they started behaving under gravity, and you can show that just with gravity you'll find the huge amount of structure which we saw in those first few slides. We saw so much structure in the universe, they are just formed by gravity. And here is a slide. You see that how this is working. This movie will keep playing. You will have the initial set of density fluctuations. Now this Z which is there, so Z is just a marker, it's called redshift. It measures the age of the universe. Higher Z means younger universe. You see that gravity is pulling things towards each other and making things much, much more dense. As you see that at Z is equal to 0, that is our today's universe, it is actually looking a lot like, what we see, lot of density, and much of the empty spaces are very empty. So that is the action of gravity, that very homogeneous thing, which is what we saw, we already have observation for, has become the structure which we see. Now, one thing which we do have in our hands, that is to say, the kind of things which we are made up of, the kind of things whose physics we understand, is known as, they are atoms, they are also known as baryons. That's the technical term. In this talk, I will use both the terms, atoms, baryons, interchangeably. But what is very humbling for us, of course, is that the amount of material which is there in this kind of species which we do understand, all these things are made of atoms, is only 5% of our universe. So just 5%. And the rest of the universe is in this exotic dark matter and dark energy. Maybe you've heard about them. These are things which we haven't really seen in the lab, neither we have a very good theoretical understanding of. So these are the biggest open questions in cosmology, the nature of dark matter and dark energy. But the interesting thing is, we only have our atoms to unravel this mystery. So if you see the baryons itself, now if this picture humbled you, the other picture will humble you even more, because this kind of baryons, we can also make a budget of that. Now this picture is technical, so don't worry about what it's showing, just worry about this. The kind of, even out of this 5%, only less than 10%, about 7%, is there in actually the baryons which we think as stars, galaxies, what we are made of is actually even less than 10% out of this 5%. So actually the atoms, if we want to study, we have to study them as gas, because in the universe the atoms are mostly gas, and they are gas at different forms, different phases, and so on. So if you see the way the baryons evolved over time, then we would like to understand what were like the milestones. So we want to see how the baryons evolved. So here is kind of like the a kind of chart of how these, there were two major phase transitions. So the first one is the recombination, which is what happened around 300,000 years after the Big Bang. We saw that the radiation and matter had a decoupling. So what happened was, before that it was all ionized, and then you had this 300,000 years after the Big Bang, you had it to come together. At that time, the radiation, which we see still as cosmic microwave background, and the neutral atoms, mostly it was hydrogen, those are, those have parted company, and at that time things were all neutral. Then started what is known as the dark ages of the universe. So dark ages because there were no stars, no galaxies, everything was dark. So we only had neutral hydrogen, and that kind of formed the first stars, first galaxies. And then came this interesting epoch, which is known as the cosmic dawn. So this cosmic dawn, which is also called as first light, when the first stars, they lit up the universe, literally. They lit it up, and they resulted in what is called the next phase transition or transition of these mostly hydrogen, which has happened around about 1 billion years after the Big Bang, and that is known as cosmic reionization. So this reionization is what happened when these first luminous sources turn back the hydrogen into protons and electrons. So that is a very important frontier. It is within the reach of our observations today, and that is what I will be spending a little bit of time on. How did this reionization actually proceed? Yeah. So this movie should play. Yes. What happens here is, if you watch this movie, you'll see that there is a luminous source in the center, and then it kind of creates a lot of intensity of ultraviolet light. You'll see this blue, and it expands into what is called the expansion of the light coming from it ionizes the surrounding material. So that is how reionization happened, that there were bubbles of plasma inside, in sort of around every single one of these galaxies or stars or sources, and finally the bubbles expanded and they managed to fill the whole universe. And as I told you that as of 1 billion years after the Big Bang, the universe is fully reionized, and it has been like that for the last 12.5 billion years. So that's a very efficient process. We can see a little bit in simulation how that works. So here again I will try to make sure both of these are playing. On the right you should see both of these things. Now you should see them together. On the right you have the same one which you saw before. You see that in one source you see it reionizing, that is, it is forming a bubble, and this bubble is able to ionize the gas which is around it. The picture on the left, as you can see in parallel, many such are developing across the whole universe. So what is called as bubble overlap takes place at a critical point, and this point we actually still have to see in our observations, but we have a pretty fair idea how it works. This bubble overlap, you see most of these bubbles will expand. The red regions are high temperature or high ionization, and soon you will see that what is happening for one object is filling up the whole universe. And finally, when it becomes transparent, you see that the entire universe has become ionized. So this in a nutshell is how reionization proceeded, but we want to do better than just have it on our computer. We would like to see it happen. Actually, it turns out we can. And the reason has to do with this very interesting fact that cosmologists are a very lucky species. We can see the past, and that it has no mystery about it. When I look at any of you on the audience, I don't see you as you are right now. I see you as you were a very tiny fraction of a second before, because light takes some time to travel from you to me. So the picture I'm getting is slightly old. In our day-to-day life, it doesn't matter because we are dealing with kilometers and so on. Light is very fast. But say you are standing a light year away from me, I will see very old light, that is a year-old picture. And today indeed we have technology, telescopes to see almost 10 billion light years away. More than that, even today with the James Webb, we can go much further, almost up to a few 100 million years after the Big Bang. So we are seeing those as they were 13 billion years in the past. So we are actually seeing further and further into the universe, we are seeing back in time. So that is very, very nice. One of the things which was used a lot for this purpose and still being used is what we saw in the beginning of the slides, what is known as quasars. These are the objects we saw in the very first animation, which were about 5 billion years, light years away. They are like the edge of what we have mapped until James Webb Space Telescope, of course. And what is interesting is that you can see a large, whatever is in between us and the quasar. So quasar are like distant point sources. That will imprint its signature on the light from the quasar. So just like you have an absorption spectrum in the laboratory, you may have seen that when you have spectra, you have light, the material absorbs certain frequencies. We were able to figure out when the universe was ionized in the way which I told you. Now even things have become more exciting. there is the radio frequency band, which has a huge amount of promise being unlocked to explore this reionization, these bubbles, and this cosmic dawn, and so on. And one thing which it does for you is that, just as the main nutshell is that just as we have our radio, we have our frequencies which we get from the Earth. Similarly, a radio telescope, what it does is to concentrate the radio frequencies from the space, from many galaxies, from cosmology. And interesting fact is that I told you about this cosmic microwave background. This cosmic microwave background is actually it will come into your analog TV, not digital one, as a very small amount of noise or static on top of the signal. So, as we know, the main dominant element of our universe is hydrogen. That has been the case all the time, and it is the hydrogen which underwent all this reionization and so on. Now, hydrogen has a very interesting signature in the radio frequencies. It is known as 21 centimeter. Maybe some of you have heard about it. In your radio, for example, you have these kind of megahertz wavelength and so on, right? So what happens for hydrogen is that it has these two states. So it has a lower state and an upper state, and they are characterized by the spin of the nucleus and spin of electron being either parallel or antiparallel. Now, if the hydrogen, the electron jumps from the top state to the lower state, it will emit light. And if it emits light at a particular wavelength, the wavelength is 21 centimeter. And that is why this kind of transition, in the lab you won't be able to see it, because according to quantum mechanics, it's a highly forbidden transition. It can't be, it's extremely improbable, but in the universe, the sheer numbers, there are so much of molecules of so many atoms of hydrogen that you will be able to get a large amount of them having this transition, and from which you can see images of galaxies in the radio frequencies. You can't see it, it's invisible, but it is there in the radio part of the electromagnetic spectrum. People have used it a lot to map galaxies. Here's a fun picture where you can see the night sky. If you could see at radio frequencies, then you can see actual jets. You can also see aeroplane jets. It's a very interesting picture. You'll be able to see completely different things if you are able to see, in this radio band. Just to let you know that, as most of you also are aware, the radio part of the spectrum is really at the long wavelength range, and there are all these different bands in the radio. And if you look at a galaxy, you see on the left, any galaxy, this is one example, in the visible light, in optical. So what we can see if we see our own light, and in the radio extends a lot more than the optical. You see that there is a lot more. So that is a way to probe parts of the galaxy which you don't see in optical. So that is another advantage. And the reionization especially is very well probed by various experiments which are operating with radio telescopes. There are big arrays of these experiments. One of the biggest ones is the Giant Meter Wave Radio Telescope that is in Pune in India. Then there is other efforts which are constructed in Netherlands and Canada and various other places. You can see some, but by far the biggest one is called the Square Kilometer Array, or SKA. Now this SKA is an international venture. It's an intergovernmental organization. Many of the countries are part of or just about to become part of SKA, which are India, Canada, Switzerland. Several of them are part of it. What is the interesting, the main feature of this facility is that, as the name suggests, it's 1 square kilometer of telescopes, 1 square kilometer of dishes. And this will go and probe the epoch of the cosmic dawn and the first galaxies. So that's very exciting. You can go to the website of Square Kilometer Array to get more information about the telescope. And this is just some really fun facts which are there. We can see more inside on this website. For example, a single day's data would take about 2 million years to play back on an iPod. A huge amount of data is upcoming into the square kilometer array. The two arrays will be in South Africa and Australia. And just a few years ago, I learned this word called exabyte. Exabyte is 5 exabyte is every word ever spoken by any human being from the beginning. So that's the amount of information. So in 5 exabyte are all those information, and this square kilometer array will have 11 exabytes passing through it every single day. So it's really a huge venture. That's why it's an international one. And it has more data than the entire internet you can imagine in 2020 per day. So that is quite interesting, and that also means that we have a lot of scientific challenges coming up with this kind of venture, right? So the first one is, as I was telling you about the cosmology, the study of the universe. As we zoomed out up to a point, we didn't zoom out completely, right? We stopped when the galaxy survey stopped. But now we will zoom in. Again, if this thing works, yes, we are going to zoom in into one of the galaxies and look at this 21 centimeter of hydrogen. So as I said, hydrogen is usually on the outskirts. There is gas in the galaxy. This gas will emit, and its rest wavelength is 21 centimeter. But we already know this galaxy is far away, so there is a redshift. We saw that it shifts to the red. So the color will really be shifted. They are showing in color, but you can understand it's all radio frequencies. It's coming into our telescope, and this will allow us to make a map of that galaxy. It will make a map of that whole system. And what you can now see is that as you have different distances at which the galaxies are located, you will be able to make maps at different frequencies. Because as the galaxy is farther or nearer, the redshift will tell you about the place where it's located. So not only you have the map of the galaxy, you also have the 3D view, the distance to it. That is precisely why the square kilometer array is useful for tomography. So this is called the 21 centimeter cosmology. That's why it's becoming interesting. You see the whole universe, you see that what it is, you had this reionization, I told you, cosmic dawn, I told you about these things. And you can map all these interesting milestones of the universe just by tuning different frequencies in your radio telescope. Because as I said, each frequency is a different redshift, a different epoch. At each epoch, you will have a two-dimensional picture of what is happening there. Those of you who are familiar with the medical field will know this thing called PET scan. So it's called positron emission tomography. Now the T in it stands for tomography, which is like a 3D picture. Now that's exactly what we are doing here. We are taking a 3D picture of the universe, and that is one of the reasons why we are going to obtain hugely more information. So whatever information today we have, if you think of it as one book, then you will have 10,000 books worth of information if you are able to map out the entire universe from our edge to the edge of the cosmic microwave background. In some sense, you can also think of it somehow as the slicing Swiss cheese. So you have different bubbles, as I told you, the reionization and so on. So you can actually see those happening because you are taking a tomographic picture in this 21 centimeter. So that is one of the ways in which it will be very useful. And recently, some of our work has been focused on using this hydrogen and its distribution to understand, how neutral hydrogen is distributed and make predictions for telescopes and the next generation facilities. And this can be done using whatever data we have today. And we are able to definitely make cosmological predictions, but on the ground there are challenges. The 21 centimeter, the intensity mapping which I told you of getting this tomography is not really easy in practice. The main challenge is that if you see, the signal which we want is very, very tiny, and what is sitting on top of that signal is about 100,000 times brighter. And that is kind of nuisance, that is noise for us, that is some kind of emission which is there from our galaxy, that is noise in our instrument and all that. And several very clever people are definitely working on trying to eliminate those and clean the signal, but it's a needle in a haystack, right? Originally in 2018, they actually claimed that they found the first signal, and that was a big result because that was from Cosmic Dawn. This was what was found. The slide is technical, you don't have to worry about it, but the telescope was very simple. It looked like this. And the Redshift, which is here 17, which is written around about 500 million years after the Big Bang. That was the time when they said they saw hydrogen. But some more experiments, including one from India called as SARAS, were finding that this result may not be a signal. It could be some feature of the instrument. But what is more important is for us to look at the date here. This is very much an emerging field. It's 28 February of 2022. That was when this was written, and that work is going on it even today. So it's a really emerging, really timely field, and this is something which SK will shed a lot of light on. And people have definitely gone back and forth, and there is a lot of activity. There is one thing which I will mention for those of you who are interested in the James Webb Space Telescope. There was a couple of slides which I will skip in the interest of time, but I will just tell you that today we have also the same epoch, the same first light, Cosmic Dawn, in the optical, in the light which we can see thanks to the James Webb Space Telescope. I think many people must have seen these beautiful images. And what is also interesting is that intensity mapping which I told you about hydrogen also extends to other lines. So other species, carbon, oxygen, those are being used a lot when there are stars. So whenever you have stars, you will have this carbon, oxygen, carbon monoxide, and those are the ones which are being used called sub-millimeter, because that is the rest wavelength, to look at the cosmic dawn and to understand the first galaxies. I will just end by telling you about a few of the most fundamental physics questions which we can hope to answer by using the 21 centimeter and by using the James Webb and so on. The first one is, I told you about the 1 over 10 to the power 32, that is 1 followed by 32 zeros, the really first part of the universe which we didn't understand because we don't yet have a quantum theory of gravity. It turns out that there is a signature of that period which is known as cosmological inflation, and theoretically this inflation leads to different kinds of maps. So for example, if you have the inflation taking place in a different way, there's a parameter called primordial non-Gaussianity which will change, and that effect can be seen in this hydrogen map. And if you are able to measure that and remove all the other sources of noise, you might be able to shed light on how this first earliest inflation happened. So that is again very exciting. What is dark matter made up of? Again, we don't know. Some of you who were there today at the lecture would have seen that the WIMP model is kind of on its way out, whereas the axions are becoming more popular. Now, depending on what the dark matter is, there is an effect which we also worked on a little bit on this 21 centimeter. You can see that when the dark matter is different, the 21 centimeter hydrogen will be differently behaving because it's influenced by the gravity of the dark matter. You'll get different signals. So that is one of the things which we can shed light by using the 21 centimeter. That's a really fundamental question. And another one, was Einstein right? Now that is interesting with the square kilometer array because the radio telescopes which you see, they detect electromagnetic beams from spinning objects. They are known as pulsars. And this can be used to make the strongest tests of gravity near the black holes. So the black holes, we can really go and measure them with this upcoming instrument, and they will be allowing us to ask the question whether general relativity needs to be modified or it is still passing those tests. And indeed, are we alone? The cradle of life which is there, which is detectable along the radio frequencies, and indeed you can see radio signals from the first dozens of light years away, right from with the square kilometer array. So that's also a very important question which can answer. So that's it. Let me conclude by just telling you that we are able to observe the furthest and earliest galaxies and the early epochs, which is the cosmic dawn, dark ages, which are invisible. They are invisible in the normal light, but they'll be visible in the radio. There is a huge amount of neutral hydrogen there because hydrogen is the most abundant element, and we have a large amount of neutral hydrogen after the reionization took place, so just at the cosmic dawn and so on. And to see this neutral hydrogen, there are next generation radio telescopes, especially the Square Kilometer Array, which is the biggest venture coming up in this decade, actually, within a few more years. And this is very interesting to understand the distribution of neutral hydrogen, about which there are bubbles and the kind of topology of the universe and kind of a tomography. And this, also very important is today when we have this James Webb, there are some outstanding questions. I should just say a little bit that the James Webb Space Telescope detected large number of galaxies at early times which are too big and they are too bright. And those two questions are either solvable by astrophysics or cosmology, but exactly what the answer is will come forward just by using synergies with the new telescopes in the radio. And we can really answer and hope to answer the biggest cosmological questions by exploring this invisible radio universe. Thanks a lot. I'll stop here and take any questions.